Over 40 years ago, Edwin Chandras invented the glow stick. A glow stick is a single-use translucent plastic tube containing isolated substances. For a glow to be produced by the glow stick, the fluorescent dye and a form of oxalate mixes with hydrogen peroxide, which is kept in a separate compartment. This reaction releases energy and excites the electrons in the fluorescent dye to a new energy level. When the electrons come back down to their original state, they release energy in the form of photons, which produces light. The photon is represented by the orange wavy arrow. Glow sticks are commonly used for recreation and entertainment purposes. They are frequently used during celebrations, festivals, and dances. However, they have been used as a light source for the military, police, fire, or EMS operations. The reason being, glow sticks are waterproof, do not use batteries, generate negligible heat, inexpensive, and are reasonably disposable. Furthermore, they do not require any electricity to do work and do not create any chance of sparking. Therefore, glow sticks are the only source of light that is ideal and safe for use immediately following an earthquake, hurricane, tornado, or other catastrophic emergency situations, such as a blackout as shown by this episode of Big Bang Theory. For our chemistry project, we wanted to explore how temperature affects the brightness of glow sticks. We hypothesized that the higher the temperature, the brighter the glow stick will glow. This is because, according to collision theory, as temperature increases, so does the frequency of collisions between particles. This increased frequency of collisions or rate of reactions increases the brightness of the glow stick. Our dependent variable is the temperature of the glow stick. Our independent variable is the brightness of the glow stick. We have a variety of control variables. For instance, we will be using the same commercial glow stick. In addition, they will all be in the same color. Our experiment will test the brightness of glow sticks with varying temperatures. The materials needed is 3 1,000 milliliter beakers, 9 commercial glow sticks, distilled water, ice cubes, 1 water boiler, 3 thermometers, 1 marker, 1 roll of masking tape, and 1 light sensor, which will give a numerical value for brightness in the units of voltage. Procedure: wrap masking tape around each of the glow sticks and using a marker, label them A, B, C, D, E, F, G, H, and I to keep track of them. It is imperative to have 9 glow sticks to ensure that there is an adequate amount of trials to provide enough data to prove our hypothesis. Label each of the 3 1,000 milliliter beakers room, hot, and cold. Then, fill the room beaker with 1,000 milliliters of distilled water. Then place a thermometer inside the beaker. Crack the glow stick A, B, and C before placing it into the beaker, and allow them to rest in the beaker for 15 minutes. Make sure, for each trial, you allow the glow stick to sit in the beaker for exactly 15 minutes. This is to ensure we are only testing one variable. Attach the fiber optic probe by slipping the connector of the fiber optic probe over the light sensor. Adjust the sensitivity of the sensor using the sensitivity adjustment knob. We set ours to minimum because the light sensor was too sensitive when set on a higher setting and the values fluctuated too much. Hook up the light sensor into the laptop. Open up Data Studio. Before taking glow stick A, B, and C out of the beaker, record the temperature of the glow stick in the data table. Make sure you turn off the lights and it is completely dark. Place the light sensor as close to the glow stick A as possible. Make sure the light sensor is on an apparatus. This will make the entire process smoother. Then, collect 30 seconds of data, as a light sensor gives a numerical value in voltage of how intense the brightness of the glow stick is. Your data collecting should look something like this. Then proceed to record it into the data table. Repeat these steps to glow stick B and C. Repeat the same steps of glow sticks A, B, and C to glow sticks D, E, and F, but instead of filling the 1000 milliliter beaker with distilled water, fill the beaker labeled cold with ice cubes. Repeat the same steps of the previous glow sticks to glow sticks G, H, and I, but instead of filling the 1000 milliliter beaker with distilled water, use a water boiler and fill the 1000 milliliter beaker labeled hot with boiling water. Our procedures were designed to answer the question, as temperature of the glow stick increases, does the brightness of the glow stick increase? By the end of our experiment, the data that we collected answered our question. As you could see, the glow sticks have varying brightness. As shown in this data table, the higher the temperature, the higher the voltage, which translates to more intense brightness. Here is a glow stick from each beaker. Glow stick G is the brightest because it had the highest temperature, whereas glow stick D is the dullest because it had the lowest temperature. It is crucial to have 3 trials for each beaker to confirm the data. Summary. Using the data collected, we calculated averages for the glow sticks in the same beaker. Then we plotted the averages on a graph. As shown, this graph confirms that as temperature increases, so does the brightness of the glow stick. This data confirms the direct relationship between temperature and brightness. This can be explained at a molecular level. When temperature increases, so does the rate of reactions, meaning particles are colliding faster and faster, resulting in particles between diphenyl oxalate and hydrogen peroxide are colliding more frequently. As there are more collisions, the brightness increases during the reaction.